Hello, and welcome to the video lecture for topic 20, Electrophilic addition part 2. So, in topic 19, we saw that how alkenes can be both weak bases and, in a sense, a nucleophile. Specifically, we encountered a reaction where a nucleophilic alkene forms a cyclic intermediate, and this was for our oxymercuration reaction. So just as a refresher, starting with an alkene, we saw how when treated with mercury 2 acetate, we had a simultaneous reaction where we form a cyclic intermediate and displace one of our acetates to form this. So what we're going to see in topic 20 is that this is actually a really common behavior for alkenes with certain nucleophiles. And the nucleophiles that we're going to look at in this topic are going to be our dihalides, X2 molecules, and carbenes, which are special and really important and a lot of fun, but that will be in the second half of our video lecture. So now, what do I mean by X2? So X2, so we'll get our new information started here. So X2 is going to be either Br2, Cl2, right? Those are pretty much what we're limited to. Iodine, I2, is not quite reactive enough to participate in electrophilic addition with alkenes, and fluorine is way too reactive to participate in electrophilic addition to alkenes. So we're pretty much limited to bromine and chlorine for the reactions that we're going to see in the first half. Now, we can do this reaction in a wide range of solvents, and the solvent that I want to consider first is what we call an inert solvent. So let's go ahead and start with an alkene, and unlike in our last video lecture, I'm going to stop using generic alkenes, and now I'm actually going to put specific substituents on them. So here on this alkene carbon, I'm going to put an ethyl group and a methyl group on one side, and on the other side I'm going to put a hydrogen and an isopropyl group, or we'll just put PR for propyl. It'll get the same point across. So we see here that we have an E-alkene that we are starting with. Now, when a molecule of X2 comes along, whether that's going to be a molecule of bromine or a molecule of chlorine, what happens is very similar to what we saw in our oxymercuration. We're going to form a cyclic intermediate. So our alkene is going to attack one of the halogen atoms, which is going to use a pair of its electrons to attack the alkene, and we're going to displace that other halogen to give us cyclic intermediate. And now we need to think about how this is happening. So right now this alkene is adding onto one face of this molecule. And so we're going to have a very defined stereochemistry in our intermediate. And what that's going to look like, we'll end up having our ethyl group on a hash, our methyl group on a wedge. We can finish up that cyclic intermediate. We lost a pair of electrons from the halogen that becomes attached, and we used a pair of electrons from the halogen that becomes attached, which just leaves us two pairs of electrons on that halogen. These electrons in this sigma bond here came from our pi bond in our alkene. These electrons that we're going to lose will make another sigma bond to our other alkene carbon. And so if we take the time to calculate the formal charge on this halogen atom, we'll see that it has a formal charge of +1. Now the stereochemistry on our other alkene carbon, we're going to have our propyl group on a wedge, and we're going to have our hydrogen on a hash. And so if we wanted to assign stereochemistry to these carbons, we would have S and S for this example. Now, in addition, we formed X minus. And now we have a situation that's once again very similar to our protonated epoxides, right? We have a three-membered ring with a heteroatom that has a positive charge. Similar to what we saw in oxymercuration, a three-membered ring with the heteroatom with a positive charge. That means our nucleophile is going to preferentially react with the carbon that has the most substitution, because our developing partial positive charge will be most stable. And in this case, it's our carbon atom that has both the ethyl group and the methyl group attached to it. While it's going to, even though it's going to preferentially react there, it will also have an equal probability of reacting at the carbon that has fewer substituents. And so we will see both products forming. And unfortunately, even though one is preferred, the difference between the two is not significant enough for us to be able to say definitively that one is a major product and one is a minor product. So if we just go ahead and show two possible pathways, we're going to go ahead and call this pathway 2 in yellow, and we're going to call the blue pathway pathway 1. Now, if I react at pathway 1, this is going to go through an SN2 type process, so I'm going to end up inverting the stereochemistry. And in reality, it comes from down below, which is the less sterically hindered side, opposite to the leaving group. That X plus is my leaving group. I've drawn my arrows not to show, without showing that, but that's really what happens. And we'll see that pathway 1 provides us this, excuse me, let's get a little bit of a pen that's slightly more cooperative, that if we follow pathway 1 in this instance, what we end up with is a stereochemical arrangement that looks like this. And so we can see the result of this SN2 attack in that our carbon that gained the second halogen ends up with an R stereochemistry, where our carbon that had the first halogen has an S stereochemistry. So this is following pathway 1. If we follow pathway 2, we'll see that the opposite is true. Our carbon with our leaving group, so now we're coming in, we're attacking through pathway 2 at our less substituted carbon. We're going to break open that sigma bond. And so now we'll see here that stereochemistry at the unaffected carbon remains the same. That's going to go ahead and remain an S stereocenter. Our pathway 2, the nucleophile in pathway 2 did a backside attack on our less substituted carbon. So here now, there's our second halogen. That's going to go ahead and push our propyl group up, our hydrogen on a hash up, and we'll see that this stereocenter has now changed to an R. This process, adding two halogen atoms from an X2 type molecule, can only happen in what we call inert solvents. What are our inert solvents? Well, that's going to be our CHX2s. So for example, CH2Cl2, CH2Br2. Another example would be our haloforms. So these are going to be CHX3, right? The most common of which is going to be chloroform, CHCl3. or our carbon tetrahalides, CX4, which is going to be, most commonly, we have CL4 or CBr4. The most common solvents that we use are going to be methylene chloride and chloroform. The tetrahalides are highly carcinogenic and are pretty much banned in most places, so we don't really see these solvents outside of extraordinary cases. What I'd like to show you next is what would happen with this process if I replaced my inert solvent with a polar protic solvent. So we're going to go ahead and clear off the board and come right back to see what that looks like. So all I'm changing now is just the solvent that I'm running the reaction in. So the first step is really the same. We have formation of our cyclic polonium, right? And we're going to gain a X- anion as part of the process. But now, instead of using an inert solvent, right, my carbon halide solvents, this time I'm going to use a protic solvent. So this can either be alcohol or water, and so I'm going to just combine those together, call it ROH, and just keeping in mind that if I replace that R with a hydrogen, it's water, same behavior, right? If that R is some sort of carbon group, it's an alcohol, same behavior. So we get to the same initial intermediate, but remember now how these alcohol solvents behave when an anion is formed, right? What ends up happening, if you recall, is that the solvent hydrogen bonds to that anion and blocks it from being able to react. And we saw this back during our study of SN1 reactions, is where this first came up. So we can imagine that that X- is now completely blocked, and our cyclic polonium, right, this positively charged intermediate we have, is just floating around in a sea of alcohol solvent, right, which is a nucleophile, right? We have a lone pair of electrons that can easily go ahead and act, right, have this oxygen atom act as a nucleophile. And so now we can describe two new pathways. So we're going to need those electrons if we'd like to do a reaction with them. So now we can go through, once again, two different pathways, and we'll see what the results of those are. And this should look really familiar to what we just saw. So if we go through pathway 1, we'll develop this oxonium, that's a result of pathway 1. Whereas if we go through pathway 2, we get the opposite oxonium. And here's that other oxonium that we would form. And again, we see how stereochemistry inverts at whichever carbon that alcohol or that solvent molecule will attack at. The final step is the same for either one of these intermediates. Another molecule of our solvent comes along, deprotonates that oxonium, and I'm only going to draw it for pathway 2 because it's the same thing in pathway 1, just a deprotonation, an acid-base step, to give us ultimately either an ether or an alcohol, depending on what that R group in my solvent is. So here now, this is the result from pathway 2. Okay, so those are the first two reactions we want to look at. Addition of addition of X2 across a double bond, or addition of X plus a solvent molecule across a double bond. Remember, the first step of the mechanism is the same. It's just a matter of what is the solvent doing to the halide anion generated in the first step? Who's going to be the better, more abundant, more available nucleophile to open up this positively charged ring? Okay, the last reactions that we're going to look at involve a special type of reagent called a carbene. So we're going to clear off the board here for a second and then come back and really get into what is a carbene and how does it add across a double bond. Carbenes are a very unique reagent. And what makes them so unique is the structure of a carbene is a carbon atom with 2 bonds, 2 electrons, and no formal charge. So let's take a look at what that would look like. So here's my carbon atom. There are 2 electrons. I have a bond to something that we'll call Z, could be anything really. There are lots of options. And some other thing that we're going to call Z. Now, the first thing we should do is you should kind of look at this and be a little bit, wait, why isn't there a formal charge? So let's calculate what the formal charge would be. So recall that a formal charge is going to be equal to the number of valence electrons minus the number of bond pairs minus the number of non-bonding electrons. Carbon, in its neutral state, has 4 valence electrons. Here in our carbene, it has 2 bonding pairs, 1 bonding pair, 2 bonding pairs, and it has 2 non-bonding electrons, 1, 2. So we see that the formal charge on this is in fact 0. It has the right number of electrons to have a formal charge of 0. Now, from here we should perhaps gain a bit of an orbital description of what's really happening in this. What does the orbital of this look like? Well, we start off by seeing that we have 3 electron domains around this, and so it's reasonable for us to assume an sp2 hybridization. So we'll go ahead and put our carbon atom here. We're going to have 1 sp2 orbital, 2nd sp2 orbital, a 3rd sp2 orbital, and finally a p orbital above and below. Now, 2 of these sp2 orbitals are involved in sigma bonds with whatever our Z group is. So here are those 2 to match the picture that we're starting with. And that just leaves us 2 more electrons. Those 2 electrons are going to want to sit in the lowest energy available orbital. That lowest energy orbital is our sp2 orbital here, which leaves our p orbital empty. This is what's known as a singlet carbene, because all of our electrons are paired, are spin paired. Singlet versus triplet carbene is outside the scope of the course, but I just wanted to throw it out there so that you are aware of it. Now, before I move on to how these carbenes react, right, with alkenes, I want to take a stop and just let everybody know how important carbenes are. There are a set of stabilized carbenes that are widely applied in organic chemistry, and they are very, very frequent and common catalysts. Chemists have spent their entire lives studying carbenes and studying how to use them as catalysts or to stabilize metals for organic synthesis. For those of you who aren't chemistry heads like me, and who perhaps are more interested in the biological sciences than the chemical sciences, I would draw your attention to vitamin B1, also known as thiamine. Vitamin B1, thiamine, is in fact a precursor for a carbene. This is what it forms what's known as an N-heterocyclic carbene, which is really, really powerful in what it can do in biological systems, in doing chemistry in biological systems, right? And it's actually, its fundamental properties, this is the last little note I'm going to give you, right? The function, its biological function and its biological properties were actually first discovered by an organic chemist by the name of Ronald Breslow, who did these studies on thiamine back in 1958. For those of you who would like to learn a little bit more about thiamine, how it can be turned into a carbene and what it does for us, please feel free to come by and talk to me. I find it to be a truly fascinating topic, which very nicely bridges the worlds of organic chemistry and biology. Moving on to our reactions of carbenes, right? So next thing we need to know is how can we form these carbenes, right? So there are two ways that I'm going to be primarily concerned with you knowing for the formation and use of carbenes, right? One is known as the Simmons-Smith reaction, which we'll see in a moment. The other is known as use of dichlorocarbene. So dichlorocarbene is going to be one of these times where we see one of our fundamental rules get violated. And the fundamental rule of you can't do elimination on a methyl carbon. Well, it turns out that if you start with chloroform, let's get all of our electrons in here. So if you start with chloroform and you treat that with sodium hydroxide, the pKa of the hydrogen on chloroform is approximately 25. So while it isn't like a really strong acid, it's a lot stronger than most of our alkanes, which are in the range of 40 to 50. And that lowered pKa is a result of the electron withdrawing effect of the three chlorine molecules that we have here. So even though this equilibrium isn't particularly favorable, there is enough of this carbon anion being produced that in a second step, so let's just get our, here's our deprotonated chloroform. In a second step now, what can happen is that a chlorine atom can simply fall off through a process known as alpha elimination to form, oh, we had water here as well, to now form dichlorocarbene, and sodium chloride. So those are our byproducts from this sodium chloride, water, and we formed our key reagent that we want to use, dichlorocarbene. Now, before we see how dichlorocarbene reacts with an alkene, I'd like to take a moment and talk about dichlorocarbene and why we learned this on paper, but we pretty much never use it in the lab. So, dichlorocarbene is ridiculously dangerous. First of all, it is extremely pyrophoric, right? As soon as it starts to see moisture, it likes to catch fire. So that's a big problem number one. It is ridiculously explosive. Once dichlorocarbene comes into contact with carbon, and there's too high of a concentration of either the carbene or carbon around, explosion, boom, bad news, we don't want to do this. If dichlorocarbene comes into contact with oxygen, it reacts to form phosgene, which is a toxic nerve agent. It is a gas used in chemical warfare and banned by the Geneva Convention. For all of these reasons, dichlorocarbene is a really, really bad reagent for us to use. But we do occasionally do it under very, very controlled and special circumstances, so it's important for us to learn how it works. The end result of the message is, unless you're looking to go to a hospital, don't mix sodium hydroxide and chloroform together. It just ends badly if you haven't spent your entire life working in an organic synthesis lab. Okay, so now that we've formed dichlorocarbene, let's get a little space on the board and we'll see how it reacts with alkenes. All right, so now we have formed our dichlorocarbene, and we can go ahead and see how it reacts with alkenes. So I'm just now going to draw a generic alkene. I'll put 4 substituents on it. And I'm actually going to number these substituents so that we see what ends up happening. So I'm going to number them R1, R2, R3, and R4. So just like we saw when adding X2, just like we saw during oxymercuration, right? Our carbene is going to form a cyclic compound when it reacts with our alkene. In the first step, alkene electrons go to that carbene carbon. Simultaneously, the carbene electrons go to the other alkene carbon, and we end up forming a dichlorocyclopropane. And now the reason I put in these numbers on our alkene substituents is because this is a single-step concerted process, and in single-step concerted processes, stereochemistry is preserved. So what we'll see is that R3 and R2, which are on the same side of the alkene, right, will end up on the same side of our cyclopropane. And, excuse me, this should be R4, pardon me, as should this. So, once again, R2 and R4, which are on the same side of the alkene, end up on the same side of the cyclopropane. And R1 and R3, which are on the same side of the alkene, end up on the same side of the cyclopropane. So again, we have stereochemistry conserved during this cycloaddition reaction, right? Or during the formation of this cycle. Now, after my little diatribe about why dichlorocarbene is a terrible reagent and extremely dangerous for us to use, hopefully your natural next question is, but Sam, what if I want to make a cyclopropane using a carbene and I don't want to risk sending myself to the hospital? Well, fortunately, we have another set of reagents, as opposed to chloroform and sodium hydroxide, that allows us to do this. This reagent combination has a name. It's known as the Simmons-Smith reagent or the Simmons-Smith reaction. So, in a Simmons-Smith reaction, we are able to use zinc to form a carbene. The arrow pushing of which is not so important. More so, I'd like you to see the transition state and the overall transformation. Now, Sorel and Pogel get close to what we do in real life in this modern age of how we do the Simmons-Smith reaction, but they don't quite get it right. So nobody ever really uses zinc-copper amalgam to do this anymore. And, well, we actually use a different zinc reagent, diethyl zinc. And so I'm going to show you how this process goes. Again, I want you to be aware of the transition state, but specific arrow pushing is outside of what I need you to know. So we begin with this diethyl zinc reagent. And we combine that with diiodomethane. So here's my single carbon, 2 hydrogens, 2 iodine. We use something called a non-coordinating solvent. Typically, this is toluene is our solvent. So there's toluene, our solvent. It's not going to do anything, but it's good to know that we typically tend to use non-polar solvents for this reaction. And in the first step, what ends up happening is there's a little bit of shuffling of atoms around, and we generate an intermediate where we have zinc bonded to this diiodomethane, and we also form ethyl iodide as a byproduct here. At this point, we can add to it our alkene. So here now I'm going to add my alkene. And we'll go R1 this time, R2, R3, and R4. and we develop a transition state that's known as the butterfly transition state. So what does that look like? So here now we have our zinc. We have a partial bond to this iodine, a partial bond to the carbon atom, which is formally still bonded to both hydrogens. We have a couple of partial bonds to our alkene carbon. That pi bond is now beginning to break. And we have stereochemistry of our alkene is preserved. So this is known as the butterfly transition state of the Simmons-Smith, the end result of which is we produce here now this zinc iodide, or this ethyl zinc iodide, and our cyclopropane. We have done so in a fashion that does not expose us to unreasonable levels of danger, and we have done so in a fashion that preserves the stereochemistry of our starting alkene. So here R1, R2, R4, and R3. All right, so that takes us to the end of topic 20, where we saw how X2 adds in two different ways to an alkene. It either adds as one halogen on each of the alkene carbons, or if I use some sort of polar protic solvent, I add a halogen to one alkene carbon and an oxygen to that second alkene carbon. And we've seen how we can make cyclopropanes. We can make dichlorocyclopropanes using dichlorocarbene, which is a very dangerous way for us to go, or we can make standard cyclopropanes relatively safely using diethyl zinc and diiodomethane. All right, so that's the end of topic 20. And as always, thank you for watching. And if you have any questions, please feel free to bring them to conference, lecture, office hours, or stop by for an appointment. Thank you.